the next few chapters, we're going to get into using reasoning a lot. We're going to start off by learning inductive reasoning. We'll get into deductive reasoning, and eventually we'll build it into proving situations in geometry. So to begin, inductive reasoning is reasoning that uses a number of specific examples to arrive at a conclusion. Usually you're looking for specific examples, or you may also look for a pattern. Those are the two types of things you look for to know if it's inductive reasoning or not. Examples and patterns. And depending on what the examples are and the patterns are, we can make a conjecture about it. And a conjecture is a concluding statement reached in using inductive reasoning. Conjecture would be stating what's occurring and basically saying what's going to happen next based on what has happened previously. That's why you look for those examples and patterns. Now, let's make sense of this with some examples here. So up top, my directions say write a conjecture that describes the pattern in each sequence. Then use your conjecture to find the next item in the sequence. Okay, now we're not going to write an equation for our sequence like we did last year in algebra. We're just going to describe what happens and then use that conjecture to find the next item. So if I look at A here, well, let's try to find a pattern. I'm going from 2 to 4, then 4 to 12. Well, I added by a lot more there, didn't I? 12 to 48. So I'm jumping up pretty quick. So there's no adding pattern. So maybe let's see if there's a multiplying pattern. Well, from 2 to 4, I multiplied by 2. From 4 to 12, I multiplied by 3. From 12 to 48, I multiplied by 4. Well, it looks like we're just multiplying by the next number up, correct? So I'm guessing I'm going to multiply by 5 here. And if I would take 240 divided by 48, I would notice that it is 5. So there's my pattern. I'm multiplying by the next number. So you have to state that to me as your conjecture. So you could say something like, the term is being multiplied by 1 more than the previous term. Something along those lines. So let me know what's occurring. And then it says, use that conjecture to find the next item. Well, I'm guessing I would multiply by 6 next, right? Times 6. That'd be the next part of my pattern here. So 240 times 6 gives us 1440. So there's using that conjecture to find the next item in the sequence. Looking at the next example. I do the same thing, try to find that pattern. I usually take a look at what they're adding by right away. So here I'm adding by 6. The next one I'm adding by 9. Well, let's see if there's a multiplying pattern here. So here I multiplied by 3. The next one I multiplied by 2. I don't think the pattern is multiplying by 1 less. But it looks like this top one I got a pattern here, plus 6, plus 9. The next one you think would be what? Plus 12, which means you're adding by the next multiple of 3, aren't you? Because here I've added by 6, and then by 9, and then by 12. So you could say the term is being added by the next multiple of 3. Just something that I know what's occurring by your sentence. And then let's go ahead and use that to find the next term in the sequence. So it looks like I'm going to add by 12, right? So 30. So there's my next item according to that conjecture. Okay, we can also make a conjecture given a relationship in geometry or in math here. So list or draw some examples that support your conjecture. So I got 2 things. Make the conjecture, then let's list some examples to support that conjecture. So the first one, the sum of an odd number and an even number. Well, let me do a couple examples to figure out what I'm going to say. So an odd and an even. There we go. I get an odd. Let's try another case. An odd and an even. And I get an odd number again. So I'm guessing my conjecture would be the sum of an odd number and an even number is an odd number. So there's my conjecture, is an odd number, and there's some examples to support my conjecture. For B, now I have a geometric situation. It gives me 3 points. It says LM is 20, MN is 6, LN is 14. And let's make a conjecture. It says, and draw a figure to illustrate your conjecture. Well, let's draw that figure. So LM is the big line, big segment. So that's 20. Then it gets broken off. LN is 14, so N somewhere around there. So LN is 14, MN is 6, and they make a total of 20, correct? Well, what's something I could say about these in geometry? I suppose I could say that LN and NM add up to LM. That would be something I could make a conjecture on. I could also say, what about these 3 points? Well, if they add up to 20, aren't they all in the same line? So I could say that L, M, and N are collinear. And here's my example to support that conjecture, because they'd have to be on the same line if they add up to 20. Okay, so maybe do your examples first, because then that'll help you state your conjecture. We can also get into a story problem here where we're making conjecture. So this table shows the total sales for the first 3 months of a store, and the owner wants to predict the sales for the 4th month. So we're just looking for that pattern again. So I want to know in that 4th month what's going to happen. So month 4, 4th month. Well, if I look, what's happening here in this case? It went up 1,000. The next one, it went up 3,000. What about multiplying? What happened? 500 to 1,500, it got multiplied by 3, right? 1,500 divided by 500 is 3. The next case, is that the same thing? Yep, 1,500 times 3. So it looks like we have a consistent pattern of multiplying by 3. So to make a prediction for the 4th month, we take 4,500 and we multiply it by 3. Which gives us $13,500 for the 4th month. And to justify my claim or prediction is just right here. I multiplied by 3. I found a pattern. That's my justification. I don't need to write any words for that. Finally, we have counterexamples. It's going to make a conjecture false. So we're going to be given a conjecture or a statement, and we're going to make it false by giving a counterexample. So what it's going to do is it's going to say if some case is true, then it's going to give us something. Well, we want to say even though that case, if the if is true, we want to give it something to make this false. Get that then false. So if I look at this first one, if n is a real number, then negative n is a negative. Well, there's probably a lot of numbers I could put in for n to keep that whole thing true, that there actually is a true conjecture. But what can I put in for n to make this part false, to make that part wrong, where this part would still be true over here? Well, if I think about it, n is a real number, so that's positives and negatives. So I could say n is what? Negative 5, couldn't I? Because then if I take negative n, it's really negative 5, or the opposite of negative 5, which is positive 5, which makes that false, right? So here is my counterexample, that n could be negative 5, and it would make my then false. So just give something to show that the then is false, giving a counterexample. For B, you may need to draw a picture. It's saying if two angles are congruent, ABC and DBE, then ABC and DBE are vertical angles. Well, they could be, right, because vertical angles are congruent, right? I could have two lines like this and have A, B, C, and then DBE, right? Because then ABC and DBE would be congruent. That's true. But that doesn't have to be the case, does it? What if DBE was a little bit up out here, just like that, and these guys were still congruent? They don't have to be vertical. They both could be 50 degrees, couldn't they? So there, I just drew a picture that stated this false. So just because they're congruent and they share the same vertex in B, that doesn't necessarily mean that they're vertical. And I proved that by drawing that picture. I gave a counterexample with that picture. Okay, so the if has to be true, but you want to make the then false by giving a counterexample. That's all I got for you. Deuces.